Welcome to Lesson 3, example number 5, and what they are asking for is to size a wood beam for this structure, or this beam that they're showing here. And hopefully you notice that, hey, this is a simple beam, and realistically, in real life, you'll have one of these will be a pin and one of them will be a roller, but you'll say, okay, well, we don't have any forces in the x direction, so that will end up equaling 0, so we can just get rid of it. And this is what you're left with. And hopefully by now you've kind of looked at this, and no, it's not a distributed load, but they do have this type of loading arrangement in the your steel manual, and they've actually reproduced it here for you, so you can just go ahead and take it off of that. So let's go ahead and get the max from this. That means we don't have to go through and figure out the reactions. We don't have to figure out the moment and shear diagrams. You can just derive all those moment shear diagrams are derived and put into equations. And you can go ahead and make your shear and moment diagrams if you don't trust these equations, or you just want to verify them yourself. I think that's a worthwhile exercise to do, because you just get used to, hey, knowing where it's coming from, and not the more you know where it's coming from, the faster you're going to go and the more sure about what you're doing. So I recommend you do that. But anyways, we're going to move right on. So we want to look for Vmax, what is your shear max, and your M max. Which, if you're thinking about it real quick, let's just think what the shear and moment diagram will look like. It's going to start there. Here's your shear diagram. Actually, let's go ahead and just do it. This is about the easiest shear and moment diagram you're ever going to come across. Let's look at this. This is going to be 1500. Let's change colors real quick. And I'm not going to go into how that comes out, but you can figure that out, because it's symmetrical, and this load's going to go into there, and this load's going to go into there. Anyway, I hope that makes sense. If you have a load right down the middle, it's going to be split in half. And if you have two symmetrical loads, they're going to be split in half as well. And total, you have 3,000. It's going to be split evenly, so you have 1,500. I hope that explained it well. But anyways, we're going to move on. You can work it out and figure that out yourself if you don't trust me. And we're going to go up 1,500. We're going to go over 8 foot to 1,500, then we go down to 0. So across that middle part of the beam, you go down again. You're going to have negative or positive 1,500 pounds, and you're going to have negative 1,500 pounds right here. So you can see that your Vmax is going to be 1,500 pounds. Well, actually, let's do the equation as well. And the equation that it gives us is R equals V. That means your reaction equals your shear, and it equals P. And your P, if you look on the little diagram, is 1,500. So we were right. Let's actually call it P equals 1,500 pounds. All right. Then it says M max. Let's go ahead and figure it out. It says between loads, M max, and that'll be that'll be obvious real quick. And it says PA, and A is, I believe, if you look at the diagram, is going to be your 8 foot. But I'm going to double check, because I don't want you to give you bad information here. And it is. It's the distance to A. A is this. If you look on the diagram, and it's that distance right there. So it's PA is what it says. So we say, okay, well, P is a 1,500. That's what it says on the diagram. So that's 1,500 pounds times A, which is 8 foot, equals, get my handy calculator out, 1,500 times 8 equals 12,000 foot-pounds. All right, so let's go ahead and do the moment diagram here to verify that, hey, this equation is correct. And it says between the two loads, so here, and that should make sense. We're going to be going up. We're going to be going up at a positive 1500x slope to this point. And then we're not doing anything. It's at 0 until you get to 8, and then it's going to go down at that negative 1500x. And if we do, well, it should be, that's A1, or the area, this point right here, the value, I was just looking for what word, the value, I'll say value of this point is the area under this box. And we've done this a bunch. If you're not feeling comfortable, and we'll call this A1. And you can go over here and say A1 equals 1,500 pounds times 8 foot, which that's exactly what we're doing there. 8 foot equals 12,000 foot-pounds. That is not a good handwriting, I apologize. But that's alright, we're going to move on. Foot-pounds. And that's the same, 12,000, and then it goes back down to 0, because this is negative. So you're going to have a negative slope. And we've done a few examples of shear moment diagrams, and I will eventually do a lot more, but I'm running through this study guide, and this is just the examples I'm doing. So very important that you get this, where this equation right here comes from. And it should make sense. Oh, okay, yeah, that's how they got PA. So we've got our reactions, which equals V max is 1,500. We've got our M max is 1,200 pounds. We also need to get the deflection. And we want to figure out what our deflection, because those are the three main, in timber construction, the three main things you want to go after is you want to say bending or flexure. Same thing, well, flexure. I'll do it bending slash flexure. It means your stress and bending. And then you have shear. And then you want to check deformation. So number one, design for this. And then check these two to make sure. Because typically your bending is going to, for beams especially, 99% of the time, let's say, maybe not 99, but most of the time you want to design for your bending first. And that's a good way just to learn and think of it as strength, so it doesn't fail. And maybe later on you'll start, for instance, we'll do a long span steel bridge, and we know it's going to deflect a lot, and that's what's going to control. So sometimes we design for deflection, and then we go back and we know shear and bending are going to be good, but you go back and check them. But for all intents and purposes, you want to start with bending and flexure. Design for that, and then check the other two. So let's go ahead and do that. I guess we can move down and get a little bit more space here. All right. So we'll do bending first. Bending. And we know that, well, we have two things. You have your capacity, which is capital F, stress and bending, and you have your load. And we know that this right here equals MC over I, or M over S. And that's what we'll go with. If you don't have S, you do MC over I. And then you need to figure this out for wood, and that's where you can go back to these tables that they have provided for you, where you can find it in a UBC or whatever code you're looking at. And it looks like the capital FB on the lower table, it says select structural beams and stringers, and FB is rated at 1,600 PSI. FB equals 1,600 PSI. Remember, this is capacity, and this is load. And you need this capacity to be larger than the load. All right, so let's move on here. And remember, we want, if we can say this is the max, you could say this is max, your max stress. So what we want to do is we want to kind of put this in here for the max, for here and say, okay, well, if we had our max stress, what is our minimum S to get that max stress, since it's inversely related? So we can go over here and say, all right, PSI equals M, which we know M. Our M max is 12,000. Now let's look at units, because you start doing this and you need to really look at units, that you're not getting to a point where you're mixing feet and inches. That's going to be your main. And we're solving for S. And since that the bigger S gets, the stronger the beam is, so you'll know that's S min. Hopefully that makes sense. This is your max stress. So you want you're going to look for your minimum section modulus to give you that max stress, and I'll show you that in a second. So we had M over S, 12,000 pounds. Typically we'll want this in inches to the third, so we want to make this go into inch pounds. To do that, you say, okay, I want to put foot on bottom, and that's 1 foot equals 12 inches. And we get, solve for S, which means S is going to go over there, 1600 is going to go over here, and you get S min equals 12,000 times 12 divided by 1600, and you get 90 inches to the third. And as long as you're, let's make sure we have foot divided by foot is cancel out, so we have inch pounds, and we put this over here, so we have inch pounds divided by pounds times inch squared will give you inches to the third. I hope you followed that out. If you don't, I'm sure you can figure it out. It'll just take a few minutes. I'll do some videos on it later, but I don't want to waste time on that. Alright, so we have 90. Now we need to go to the tables and figure out, okay, what section has an S of 90? So we look at page 45 in the study guide, has our table that we're looking for, and let's look at the S's. Just kind of go straight down. You look at section modulus, and of course we're talking about the x-axis. That's going to be our strong axis. And you can do a 3 by 16, looks like 96.9. You could do a 4 by 14, and I know in the example they did a 6 by, well, we'll do it 6 by 12. Is that what they did? Yes, they said 6 by 12. And I would agree with them. And I guess you could do other things, but I'm guessing wood, if you look at the A, you want to do the smallest A because that's your most economical beam. And that has a 63.25. And the first one we came about was 38.13. I guess that would work. But anyways, they chose a 6 by 12. Do I know why exactly? No, I do not. But I'm going to go ahead and choose that. It works. Officially, other things would work as well. But you choose 6 by 12, and it has an S equals 121.2 inches to the third. And let's go ahead and do the I as well, because we're going to need it for deflection purposes. And I equals 6 by 12, I equals 697.1. And that's going to be in inches to the fourth. Alright, so that is our design. Let's go change colors and circle it or square it real quick. So we have done this right here. We have designed for bending and flexure. So this will work. Now we need to check shear and deformation, and I'm going to wait until the next video to do that because I'm running low on time. So I will see you in a second.